Yeah, I'm having trouble with students not being able to, I can't hear some of them. And they turn on their microphone, I still can't hear them. I got my volume turned all the way up in Zoom. When I get out, I'm getting ready to go to another class in about 4 minutes. So you think we could check it after 12:30? Well, let me check that and see. I'll try that and see what happens. Mhm. I'll take a look at it. So I know the volume's up. So, okay, I'll check that. Thanks. Bye.
Hi there.
Hey, Cam, how are you?
It's just you and me now.
I guess so.
Is this Jillian? Is she working part time now or what? Or full time or?
Hang on a second, I want to turn off my mute. Okay, let's go ahead and get started. First of all, can you hear me? Can anybody hear? Okay, thank you. Thank you. So, because I'm having some trouble with the microphone in this end. So we're going to continue our discussion on mixtures and solutions today. Lab this afternoon, we are going to finish the second half of Unit 1. I think that's what we're doing today. What's today? Today's the 31st. So we've only had, yeah. Yes, this would be the second part of Unit 1. So we'll look at cell structure and things like that. And I know the lab schedule had a lab exam listed for today, and that is not going to happen today. I'll just tell you that. So yeah, I can see a very great sense of relief, but there is no lab exam today. So because the Monday lab is a week behind everybody. So we probably won't have the lab exam next week either. I'll probably give you another week to get ready for it. So anyway, let's go ahead and get started here on back into chemistry. And I think, this is where we had stopped the last time on solutions. I hope this is where we stop. This is where I want to start. So, and let's open this up. Everybody should see the slide that says solutions. And okay, so we were talking about solutions the other day and how we mix, how a simple solution, I think that's where we were. What's a solution? A solution has two parts. It has a solvent, which is the dissolving medium, which is usually water, and it has the solute, which in our bodies is usually a salt. So if we make a solution of salt, of sodium chloride, we would take, for example, a 10% salt solution would be 100 grams of sodium chloride in a liter of water, and 100 grams into 1,000 mils. If you get rid of the units, 100 is 10% of 1,000. So that's a 10% salt solution. Or 400 grams of sugar, of glucose, in a liter of water gives you a 40% glucose solution. Yeah. Or if you want to have a 5% solution, you'd have 50 grams in a liter of water. That gives you a 5% solution. Now that is these percentages are the easiest way to make up solutions. And most solutions that you encounter in healthcare are going to be based on percentages. Whether it's a 10% glucose solution or a 5% salt solution or a 0.9% sodium chloride solution, which happens to be the same percent salt as found in plasma. And we would call that normal saline levels. So that we use percentages just about all the time when we're making up solutions in any kind of healthcare environment. Now, the other way we measure solutions, and this is in very specific areas, it's milligrams per deciliter. A deciliter is 1/100th of a liter. And so how many milligrams of a substance do we have in a deciliter? Well, it turns out that usually we measure blood sugar levels in milligrams per deciliter. You know, the average, the healthy level for blood sugar should be around 80 to 100 milligrams per deciliter. We measure that as blood glucose. And, if you've ever had your blood work done, you don't eat anything the night before and nothing in the morning, and then you go in and they draw some blood, and then they tell you a couple days later, well, your blood sugar level was at 85, or your blood sugar level was at 350. You know, we need to see you right away, that kind of thing. Generally, the units, are milligrams per deciliter. Only a few things that we use milligrams per deciliter in, because most of the solutions we deal with are going to be in percentages. Okay, now the third category of solutions is called molarity. Molarity is used a lot in chemistry. A mole is, if you take the molecular weight of a compound, so you add up the atomic weight of all the atoms in a compound. So for example, sodium chloride, the molecular weight for sodium is 23, and the molecular weight of chlorine is 35, and that gives you 58 if you add those two together. So the molecular weight of an atom of sodium chloride is 58. If you convert that molecular weight to grams, and now instead of having just 58, we have 58 grams of sodium chloride, table salt, and put that in a liter of water, we now have what's known as a 1 molar solution. A mole is equivalent to the molecular weight of any compound in grams. That's a mole. Now, why are we concerned about that? Hang on a second, I'll explain it to you. A mole of any compound, a solution, a 1 molar solution of any compound has the same number of particles present. It doesn't matter what the molecular weight is. If you have a 1 molar solution of sodium chloride, you added 58 grams of sodium chloride to a liter of water, that gives you a 1 molar solution. Now in chemist talk, they measure the strength of certain chemicals, solutions, by the molarity. For example, a 1 molar solution of sulfuric acid is, you don't want to spill it on yourself. But a 6 molar solution, which is 6 times the concentration, would be very powerful, would burn through your skin. It would cause significant damage to your skin and, eat right through your clothing. So chemists can measure the concentration, the strength of certain acids by, is it 1 molar, is it 6 molar, is it a 0.01 molar, values like that. And if you've ever had a chemistry class previously, you've probably experienced using, solutions of acids at, a 1/10 of a mole, or a mole, or 6 moles, or something like that. Concentrated hydrochloric acid, for example, is usually a 6 molar solution. Glucose, let's take a look at glucose. Now, glucose is pretty innocuous. The molecular weight for a molecule of glucose, glucose has a formula of 6 carbons, 12 hydrogens, and 6 oxygens. That tallies up to about 180. So 180 grams of glucose in a liter of water gives you a 1 molar glucose solution. Now, despite the fact that the molecule is probably 3 times bigger than the molecule of sodium chloride, we make up a 1 molar solution of sodium chloride and a 1 molar solution of glucose. We've got larger sugar molecules than we got than sodium chloride molecules. It doesn't matter. There is a known constant here. The number of particles in solution, regardless of what the molecule is, has a constant number of particles. And that amount is 6.02 times 10 to the 23rd. So it doesn't matter if you have a 1 molar sodium chloride with the smaller sodium chloride, and you have a 1 molar glucose with the larger glucose molecule, you're still going to have the same number of particles in solution. And we call that Avogadro's number. We call it Avogadro's number. 6.02 times 10 to the 23rd. And chemists, because they have a strange sense of humor, will say October 23rd is mole day, because that's 10 to the 23rd, I guess. Why do we care? Well, it's the number of solute particles in solution that create, that drive osmosis, movement across a membrane. So more water, less water. So this is why we pay attention to Avogadro's number. So it's very unlikely that you would ever encounter molarity in healthcare. Now you may encounter molarity if and when you take a course in introductory chemistry or in microbiology, you may encounter it there. But it's pretty unusual to encounter molarity in healthcare. But it does help us to understand what's going to drive the movement of water from inside a cell or outside a cell. So what do you need to remember? Avogadro's number is 6.02 times 10 to the 23rd. Okay, so, and a mole is the molecular weight of any compound in grams. Okay. So that's a solution. Now the second type of mixture. Now remember, a mixture, the ingredients of a mixture are only physically intermixed. There are no chemical reactions taking place. They have not been changed. With a mixture, you can actually separate out the components. With an emulsion like milk, you can filter out the water and the fat and theoretically the protein and the sugars. If you had a filter small enough, which there are many filters available like that. If you have a saltwater solution, you can filter out the salt given a small enough filter. So it isn't like, or a sugar solution, you can filter out the sugar. There is no physical change to the ingredients in a mixture. So with a colloid is also known as an emulsion. Milk is a colloid. You can't see through it. It's cloudy. It's not transparent like a solution is. Transparent solutions are always transparent because the solutes are always floating around in solution. The solute particles are always floating in solution. You can't see through the solute particles, so the solution appears to be transparent. A Coke or a cup of coffee or a lemonade or any kind of like Gatorade and all like that, they're solutions. They're all transparent. You can see right through them. They may be colored, they may be caramel colored, or they can be yellow like Gatorade, or orange like Gatorade, and or yellow like Mountain Dew, or they can be like tea or coffee. They are still transparent. Colloids are not transparent. You can't see through them. They are what we call opaque. They're cloudy. Milk is the classic example of a colloid. You can't see through a glass of milk. It has butterfat floating throughout the water that makes up most of the milk, but the butterfat doesn't, is visible. And so you can't see through it. And of course, that's the emulsion or the colloid right here. The particles are so big. The butterfat, like in the case of milk, the butterfat particles are so large that they prevent light from going through there. And then the third category is the suspension. Suspensions are mixtures that will separate out over time. You mix together sand and water. You're putting together a fish tank. You have a new fish tank you're setting up, and you put in 3 inches of sand in the bottom of the tank, and then you add 20 gallons of water to it, and the sand goes into the water, and it's all cloudy, and the sand's everywhere, and you can't see anything, and hopefully your fish aren't in there because they're not going to like that. But you give it a little time and come back and look at it in an hour or two, and all the sand has settled to the bottom. the sand was suspended in the water column for a while, and then it sank to the bottom. And now you can see it. Now you can see through the tank. The water's on one level and the sand's in the bottom. Sand and water will settle out. Blood, human blood is a suspension. The red cells and the white cells and the platelets are suspended in the plasma. And on this image on the upper right side here, you can see whole blood on the test tube on the left. And on the right, same test tube after it's been spun down in a centrifuge or just given enough time to settle. The red cells and the white cells, this little layer here is the white cells. The red cells and the white cells separate out and leave the plasma behind. Now, if you shook it up again, it would mix, then it would settle out. Or in a very simple comparison, think of Italian dressing for a salad. You shake it up because you got all the spices and ingredients in there. You shake it up and they go into the into the vinegar and the water base of it. And then the oil comes to the surface comes to the top of the bottle, and all the ingredients move to the bottom. Suspensions will settle out if you leave them long enough. They're not physically changed. In any kind of mixture, there's no physical change, no chemical change to the properties. You make chocolate milk. You add chocolate to the milk. The chocolate particles from the syrup go into the milk, and they float there, and it's opaque, and yet you could filter them out. You add sugar to tea, you could filter out the sugar. You could even filter out the tea. The molecules that have leached out from the tea leaves, the flavors and the coloring. You could filter that out too. So in any kind of mixture, you could separate out the ingredients. You could take concrete and break it up into little tiny pieces, and you would get the sand and the gravel and the cement or whatever it goes into concrete, and separate it out, because there's been no chemical change to the ingredients. They've been mixed together and they harden, but there's been no chemical change. Compounds have chemical changes. Mixtures don't. Mixtures have no type of chemical change to the ingredients. A mixture can be filtered out. It can be separated. It can be sieved, or it can be strained, and you can get all the ingredients. But a compound can only be separated by breaking the chemical bonds holding the compound together. Mixtures can be heterogeneous. It can be a mix of any number of things, like concrete and gravel, or sand and water. But or they can be homogeneous, like a salt solution or tea or something like that. So they can be, they can be like milk with the fat particles floating in there. They can be salt water with the salt crystals floating in solution, or we can have compounds which are always like homogeneous. Glucose always looks like glucose. Glucose molecules all look the same. So it doesn't matter. Glucose looks the same, salt looks the same. Compounds are homogeneous. They look, every part of the compound is identical to every other part of the compound. Mixtures can be either or. Now, what holds compounds together? Well, those are what we call chemical bonds. Chemical bonds are not a physical bond. Chemical bonds involve the use of electrons, whether we are sharing electrons or actually moving electrons. Or are we attracted by like electrostatic properties, for example? Chemical bonds are not physical. They are attractions of the electrons. And so these chemical bonds involve sharing or actual capture of electrons or attraction to positive and negative ends of a molecule. Now, if you're an electron, you're going to spin in orbit around the nucleus of your atom. We know that the nucleus of the atom is going to contain protons and neutrons. Everything above, above a hydrogen atom is going to have protons and neutrons. Hydrogens don't have any neutrons. They just have proton. They just have the proton. That's it. The electrons are going to spin around the nucleus. Remember, whatever number of protons you have, you're going to have an equal number of electrons. Protons equal electrons. And they're going to spin in orbit around the nucleus. So you have the nucleus. Let's see here. So here we have our nucleus right here with its proton and its neutron. And let's say there are 3 protons. So we have 3 electrons. Well, it turns out that if you have 3 electrons, your first orbit or shell can only hold 2, no more than 2 electrons. So you have to put the third electron in a second orbit out here, or a second shell. So we have 3 protons and we have 3 electrons. We keep the electrons orbiting around the nucleus. Now, the closer you are to the nucleus, the less potential energy those electrons have. So these guys here, these electrons here and here in the very first, this is shell number 1, and this is shell number 2. They have to spend all their energy avoiding getting sucked in to the nucleus. Because you got 3 protons in the nucleus, and each one of these little electrons, they balance, their negative charge balances the positive charge of the proton, but there's 3 of them there, and that's a big pull on those electrons. So they spend all their energy staying in orbit. They don't break away, they don't get sucked in, they just stay in that orbit. But the third electron out here in the second shell is far enough away that it doesn't have to spend all of its energy to avoid being sucked into the nucleus. It has a little potential energy out here because it's a little further away. And so that's what we're looking at in this relationship with other atoms. The further you are from the nucleus, the more potential energy an electron can have. Now, the first shell will only hold a max of 2 electrons. The second shell can hold up to 8 electrons. And the third shell can either hold 8 or 18, doesn't matter. It just depends on what the atom is. Now, there's 7 different shells, but we don't need to worry because the atoms that we deal with, the molecules we deal with, never get past the third shell. Now let's clear this and there we go. Now let's go on to next slide. And here's a much nicer drawing of this. This is sodium. Sodium has, I'm sorry, no, I thought it was sodium, but no, it's aluminum. Aluminum has an atomic number of 13. That means it has 13 protons in its nucleus, which you see on the right-hand side there. And it has 14, little tiny number over in the right-hand side in the corner, says 14 neutrons. So it has 13 protons, which means it has to have 13 electrons. And you see here in its first shell, it has 2 electrons. In its second shell, it has 8 electrons. And in its third shell, it has 3. 2, 8, and 3 gives you 13. And that meets our definition here. of how many electrons you have. The first shell can only hold 2. The second shell can only hold 8. The third shell can hold up to 18. We very rarely have anything with 18 electrons. The outermost shell, regardless of whether it's the first shell or the second shell or the third shell, is called the valence shell. And the valence shell has the most potential energy. Doesn't matter if it's the first shell or the second shell or the third shell or so on. The outermost shell, the valence shell, has the most potential energy. Now for hydrogen, hydrogen's sort of out of luck because its only shell is also its valence shell. So the hydrogen electrons don't have a lot of potential energy. They have some, not very much. The further you are from the nucleus, the more potential energy you're going to have. So here we see with aluminum, it has only 3 electrons in its outer shell. That's its valence shell. It has a great deal of potential energy. It can, when it has potential energy like that, it can combine with other atoms. Now, the problem if you are an atom is that you want to have every one of your shells filled to the max. You want to have your valence shell filled up. If your valence shell has 8, you can hold up to 8, then you want it filled up with 8, because your valence shell is your outermost shell. If you have 2 electrons in your first shell and 4 in the second shell because you're carbon and you have 6 protons, you have 6 electrons, you want to get 4 more electrons in that valence shell because you're not stable. You want to be stable. And you're only going to be stable if you have every space for an electron filled up. That's what atoms like. They want to have their valence shell filled. Now, the first shell can only hold 2, but even then, you still want that. If you're hydrogen, you want to have 2 electrons in that first shell. It doesn't matter that you only have 1 proton and 1 electron. You still want to have another electron in that shell, because then you're going to be very stable. You want to have every shell filled up. You want to have every shell filled up if you can. And that's what drives chemical reactions, is the need for electrons need for an atom to fill up every space available for an electron. Hydrogen wants to have 2 electrons in its outer shell. Carbon wants to have 8 electrons in its outer shell. Oxygen wants to have 8 electrons in its shell. Sodium wants to be stable. So there are very few atoms that actually have their valence shells filled up the way they're supposed to be filled up. What we call the noble gases have their valence shells completely filled. Their outer shells completely filled, with 8 electrons. The exception to that is helium. Helium only has 2 electrons in its first shell, but it's still stable. This is helium. Its valence shell. It only has 1 valence shell because it has 2 protons and 2 electrons. Well, helium can't react with anything. Helium is unreactive because it's stable. It is completely unreactive. You can't do anything to helium to make it combine with any other atom. Directly below helium on the periodic table is neon. Neon has an atomic number of 10 protons, 10 electrons, 2 electrons in the first shell, 8 electrons in the second shell. Neon stuff is a gas that we use in lighting, just like helium is a gas we use in magnets and in chilling things down to very low temperatures, and of course in balloons, because it's lighter than atmospheric air, is also very stable. Neon's very stable. Helium is very stable. Neither one of these react with anything else. You can't combine neon and hydrogen, or neon and carbon, or neon and an acid. It doesn't work that way. Directly below neon on the periodic table is argon. Argon has an atomic number of 18. 2 in its first shell, 8 in its second shell, 8 in its third shell. Again, argon is non-reactive. We call these the noble gases. And on the periodic table of elements, they're on the far right-hand side, totally unreactive because their shells are filled and they're stable. Most atoms don't have a full valence shell. Most atoms have an uneven number. Oh, that's not necessarily true. Most atoms do not have a complete complement of electrons in the valence shell. If your atomic number is 7, that means you have 2 electrons in your first shell and 5 in your second shell. That happens to be nitrogen. If your atomic number is 6, you are carbon with 2 electrons in your first shell and 4 in your second shell. Or oxygen. Oxygen has an atomic number of 8. 2 electrons in the first shell, 6 in the second shell. But again, the shells aren't complete. They're not filled up. And so we say these atoms are reactive because they want to fill up that valence shell. They will do whatever they can to meet the need to fill up that valence shell. They desire, if they could think, the desire is to put a complete count of electrons in the valence shell, whether it's hydrogen with only 2, with 1 electron in space for another one, whether it is carbon with 4 electrons in the valence shell and the desire to have 4 more there to be completely stable. So anyway, these are the inert elements, the noble gases that can't react with anything. Helium doesn't react, neon doesn't react, argon and krypton and xenon don't react with anything because their valence shell is filled. Yeah. But here are the reactive atoms. Hydrogen, 1 electron, 1 proton, room for 1 more electron in its valence shell. Carbon, atomic number 6, it has room for 4 more in its valence shell. Oxygen has room for 2 more electrons in its valence shell. The sodium, atomic number of 11, 2 in its first shell, 8 in its second shell, 1 in its third shell. To achieve stability for sodium, you either have to pick up 7 more electrons or kick out the 11th electron because sodium doesn't play by the same rules. Sodium will kick out an electron if necessary to achieve stability. When we look at atoms and how they combine, they form chemical bonds. A chemical bond, of course, involves the electrons. That's why I'm spending so much time talking about electrons here. Now, we have ionic bonds, covalent bonds, and hydrogen bonds. These are the 3 types of chemical bonds that we generally encounter in chemistry in the human body. An ionic bond is an occurrence that takes place when an atom has either gained or lost an electron. If an atom loses an electron, it now it's no longer balanced. It no longer has the same number of protons and the same number of electrons. Since we're not going to be kicking protons out of the nucleus, if we lose an electron, let's say in the case of sodium with 11, it has atomic number of 11 protons, and we kick out an electron, 11 protons, 11 electrons, kick out 1 electrons. Now we have 11 protons and 10 electrons. And now we don't have an atom anymore. We have an ion because we've kicked out an electron and now we have a positive charge on us because we're not balanced. We have 11 protons and only 10 electrons. So we are a positive ion. instead of being a sodium atom. And this is true for all atoms that either gain or lose an electron. They either develop a positive or a negative charge. They no longer, they cease being an atom and are now an ion. And ionic bonds are held together. Well, we say it's electrostatic. It's sort of like magnets almost, because it's positive and negatively charged particles coming together. And all of our salt crystals are held together by ionic bonds. This is what salt looks like, this green and yellow thing going around here. The yellow ones are sodium and the greens are chlorine, because chlorine's bigger, held together magnetically because of positive and negative charges. Ionic compounds make up all the salts in our bodies. So how does it work? Well, the way an ionic bond works is that one electron is kicked out of one atom and grabbed by another atom. In this case, sodium gives up its 11th electron out there in that third shell. And chlorine has an atomic number of 17, which means it has 2 electrons in its first shell, excuse me, 8 in its second shell, and 7 in its third shell. Well, that's, 17 protons, 17 electrons. But chlorine wants to be stable also. So chlorine will grab that electron off of the sodium. Sodium gives up an electron, and now it has 2 electrons in its first shell and only 8 in its second shell. That electron, yanked away by the chlorine, goes into the chlorine's valence shell. And now chlorine has 2 in its first shell, 8 in its second shell, and 8 in its third shell. So a chlorine ion, negatively charged, has 18 electrons and only 17 protons. Whereas sodium has 11 protons, only 10 electrons, and they are attracted to each other electrostatically. It's a very weak bond, but it draws them together. The chlorine becomes negatively charged because it has an extra electron, has more electrons than protons. We call it an anion. The sodium has lost the electron, so it has more protons than electrons. We call it a cation. It is the positively charged ion. Consider if you've ever jump-started your car. The red post, the positive post, is the cathode side or cation side. The negative post, the black post, is the anode. And so when you jump your car, you put the red clip on your jumper cables on the red post and the black post on the black clip on the black post, because if you don't, bad things happen. And that way you keep positive and negative separated. The positive side is always the anion. I'm sorry, the positive side is always the anion, the negative side is always the cation. This positive and negative charge attracts the sodium and chlorine ions together, and they form a crystal, and that's an ionic bond. If you want to know what electrostatic attraction is, if you've ever used a Swiffer, you all know what a Swiffer is. When you rub a Swiffer across the floor, the cloth on the bottom of the Swiffer generates a charge on its surface. And that charge attracts the opposite charge. The dust and dirt particles have the opposite charge, and they are attracted to the cloth on the Swiffer. That's how the Swiffer sucks up all that dirt so easily, because just rubbing it across the floor, it's sort of like static electricity. You're putting a charge on the cloth, and that charge is opposite of what dust and dirt is. Dust and dirt sucked up in the cloth, and then you got your floor clean. And it's a very weak attraction, but it works on the Swiffer. It works on holding our salt crystals together. So this is what, ionic bonding. Up here in the top, you can see there's the 11th electron in red being kicked out of the sodium and being grabbed, so that we now have 2 and 8 electrons in the sodium. And over here, the chlorine is grabbing that 11th electron and filling up its valence shell with 8 electrons. Now there's our chlorine, happy with its full shell. And there's our sodium, happy without that last little electron. So now we have a sodium ion and a chlorine ion, and they are attracted to each other and they form crystals, salt crystals. That's what a salt crystal looks like. The salt crystal is nothing but sodium ions and chlorine ions attracted together electrostatically. It's a very fragile bond. It breaks very, very easily in water. Salt goes into solution very easily. And so this is what an ionic bond does. And all salts are held together with ionic bonds. And in our bodies, we're using sodium and potassium and chlorine and magnesium and calcium as ions held together through ionic bonding. So that is the simplest, well, not necessarily the simplest, but it's a very simple type of chemical bonding. Now, the second type of chemical bonding is the covalent bond. The covalent bond occurs between electrons in valence shells. Nobody's stealing anybody's electrons here. Nobody is stealing anybody's electrons. What we do have, though, is a sharing of electrons. A covalent bond occurs between 2 atoms, 2 or more atoms, using the electrons of their valence shells. So we share electrons to achieve the stability that the atom wants. The atom wants to have 8 electrons in its outer shell, in its valence shell. If we share electrons with another atom that also wants to have 8 electrons in its outer shell, we can. And since these electrons are moving at the speed of light, which is 186,000 miles per second, they can be in 2 places at the same time for all we care. For all intents and purposes, they can be moving so rapidly back and forth between the orbits of each atom that they appear to be filling up the shell of one atom and the other atom at the same time. So we fill up the valence shell, fully fill it up at least part of the time. But at 186,000 miles per second, we can't tell the difference. And so these atoms will be happy because their valence shells are filled up part of the time. Now, if we share 2 electrons between 2 atoms, we have what we call a single covalent bond. If we have, and most covalent bonds are single bonds. Some covalent bonds are double bonds where we share 4 electrons. Atmospheric oxygen is held together with double bonds. O2, you've heard of oxygen called O2. Well, that's because it's 2 atoms of oxygen, elemental oxygen held together, 2 of those held together to give us oxygen, the breathable kind. It's held together by a double bond. 2 oxygen atoms share 4 electrons. And if we share 6 electrons between atoms, we have a triple bond. Nitrogen, atmospheric nitrogen that we breathe in also, because 80% of our air is nitrogen. Atmospheric nitrogen is held together with a triple bond. Needless to say that atmospheric oxygen doesn't combine with anything else, and atmospheric nitrogen doesn't have anything else either. They're held together with double and triple bonds. Most covalent bonds are going to be single and with the occasional double bond in there. And we'll see those in a little bit. So it doesn't matter how many electrons they're sharing, they're going to be able to satisfy the need to have their valence shell filled up at least part of the time. This is a covalent bond. Here we see at the top hydrogen. Now, remember the electrons would be circling the hydrogen atom at the speed of light, 186,000 miles per second. And so you would not see the bonds. I mean, you would not see the sharing of the electrons. At any given point, you would see the hydrogen atom on the left filled up with 2 electrons, or the hydrogen atom on the right filled up with 2 electrons. But we can't comprehend that kind of speed. But we are sharing electrons. And so we get a stable molecule because we're sharing the electrons from each atom. And that changes the properties of the molecule. A water molecule, for example, is 2 hydrogens and an oxygen. The properties of the individual hydrogens and the property of the oxygen are no longer the dominant property of the molecule. The water molecule is different. It's different than the individual gases. We've had a chemical change to the molecule that's formed. Atmospheric oxygen is different than elemental oxygen. Atmospheric oxygen is breathable. We can use it. We can't use elemental oxygen. So we've had a chemical change thanks to the covalent bond. Hydrogen, atmospheric hydrogen, is a lot less exciting than elemental hydrogen. Elemental hydrogen is explosive. Atmospheric hydrogen, not so much. So, because it's a much more, H2 is a much more stable compound. Okay. Covalent bonds occur when we share electrons. And the more spaces for electrons an atom has, the more likely it is to combine with other atoms. For example, carbon. Carbon has an atomic number of 6. We see carbon right here. Here's our carbon atom right here, 6 protons and 6 electrons. Over here is hydrogen, 1 proton, 1 electron. Well, this carbon atom wants to have 4 more electrons in its valence shell. The hydrogen wants to have another electron in each one of its valence shells. The hydrogens and the carbons will come together and share their electrons so that we have a single bond here, 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 and here. This is methane. We write it as CH4, 4 hydrogens and 4 hydrogens and 1 carbon. This is methane gas. Now, what do we know about methane gas? Methane gas is natural gas. It's the stuff that we can heat with, that we can, we can power vehicles with, we can heat with it, we can cook with it. You can have a natural gas furnace, you can have a natural gas stove, you can have a natural gas hot water heater, you can have natural gas driving your powering your fireplace and your grill outside. Or we can use other gases. We can use propane. Now, but for example, why can we use methane? Well, methane, all those valence electrons now Because remember, it's sharing electrons. It's sharing all of their electrons. All that potential energy now is in the valence shell. And we can release that if we start breaking those bonds. Every time we break a chemical bond, we release energy. So what do we do with methane gas? We burn it. We burn methane. And when we burn something, we break chemical bonds and we release energy. We cook with methane, we power vehicles with methane, we heat our homes with methane, we heat water with methane. All this is natural gas and it drives, we can release the energy from it. Now, what about propane? You've probably all cooked over a propane, or you've used a gas grill. Maybe, we've probably all eaten something off of a gas grill. Now, propane is what we use on gas grills. Or if your house doesn't have natural gas lines running to it, maybe your house has a tank behind it, filled with liquid propane. Propane is similar to methane, only propane has 3 carbon atoms instead of 1. And it doesn't have 4 hydrogens, it has 8 hydrogens. So now you have a lot more electrons. This is propane right here. It would be C3H8. C3H8, because it has 3 carbons, not 1, and 8 hydrogens instead of 4. Propane has a lot more potential energy in it than methane. The stuff that we cook on the gas grill, the little tank we hook up to our gas grill, has a lot of potential energy in it. If you heat your house with propane, it's more efficient than methane. There's more energy, potential energy available in a molecule of propane because of all these extra electrons. You're sharing electrons here and 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 here. All those extra electrons gives you a lot more potential energy. So we use propane to cook with and heat our houses and power vehicles and things like that. And it works very well. So whether you have natural gas or maybe you're all electric, doesn't matter. But this is where methane and propane are great examples of the amount of potential energy stored in a molecule. Gasoline has lots of potential energy. A Snickers bar, let's talk about something we can eat. A Snickers bar, 160, 180 calories of, on the bar. What does that mean? That 180 calories is a measure of the potential energy in the Snickers bar. The carbons and hydrogens and oxygens in the sugars in the Snickers bar, you have covalent bonds between the carbons and the hydrogens and oxygens in the Snickers bar, and all those valence electrons are contributing a little bit of their potential energy, and the total amount of potential energy in the Snickers bar is measured by calories. So if it says 180 calories of energy available, that's how much potential energy that Snickers bar has. When you look at any kind of food item, it says how many calories are on it. Like a bottle of Coke, it's like 220 calories. An apple is like 60 calories. A Snickers bar, I don't know, 180 maybe. Whatever it says in the label is a measure of the total amount of potential energy in that particular food, all based on the electrons in the valence shells that they're sharing. That's why we pay attention to covalent bonding and all the electrons. That's where the energy comes from in our food. Okay, now let's So when we measure calories, that's how we measure energy, at least in food, and in heat, we measure heat and calories too. We measure how much potential energy is available in that food item or in that fuel. How many calories of energy can we release from a tank of propane, for example? How many calories of potential energy are coming from your natural gas to fire up your stove or heat your house? All these are measures of energy available. And it's all based on the sharing of electrons. Because when we share electrons, we have potential energy. Now, usually these molecules line up very nicely. Some of them have unusual shapes. Some have different shapes than others. This is carbon dioxide. Carbon dioxide lines up symmetrically. It's one of those double bond examples here I was telling you about, the oxygen and the there we go. This is one of those double bonds. We have a double bond between the oxygen and the carbon and another one over here, and they line up in a straight line. So they are sharing their electrons equally. These electrons are sharing this way and these are sharing this way. And this is a very stable atom. It doesn't usually combine with anything else. It's satisfied. It also doesn't have a lot of potential energy available. We don't use carbon dioxide as a fuel, as an energy source. However, one of the beauties of carbon dioxide is it lines up in a nice straight line, and that makes it pretty much unreactive. But let's consider what we call a polar molecule instead. A polar molecule occurs when we have uneven sharing of electrons. Uneven sharing of electrons. For example, the classic polar molecule is a water molecule. Here's a hydrogen right here. That's the hydrogen. I'm sorry, there's a hydrogen, here's an oxygen, and here's another hydrogen right here. This is your classic water molecule. Hydrogen has one electron, and we have 6 electrons in the outer shell of the oxygen. Okay, so this is oxygen. Okay, so this electron spins in orbit and satisfies the need to have, they give us 8 in that outer shell. And that's all well and good, and the water molecule is happy, if it could be happy. But what really happens, though, is that there's, oops, oh well. Is that we get an unequal distribution of the electrons. We don't lose the electrons out of the valence shell of the hydrogens. We don't lose these electrons here, but these electrons are drawn down closer to the nucleus. We tend to draw those electrons here around the hydrogens closer to the nucleus, so that we end up with a more negative charge on the oxygen end of the water molecule. There's the water molecule. The oxygen end tends to be slightly negative, and the hydrogen ends tend to be slightly positive, because all the electrons are being drawn towards the nucleus. Because you got 8 great big protons there with a big positive charge, and now all of a sudden you have your 10 electrons being pulled down there, 8 from the original oxygen plus 2 from the hydrogens, And so now you're pulling all those electrons down towards the nucleus. And so you end up with a slight positive charge on the hydrogen ends here and here, and a slight negative charge on the oxygen end. And we call this a polar molecule because it has a positive pole and a negative pole. It has two positive poles and a negative pole because of unequal sharing of the electrons. Now they're still spinning in orbit. You know, the electron at the hydrogen is still being satisfied. It's still getting its second, you know, its other electron in orbit around here. So they're happy. The hydrogens are happy. They're smiling. They're happy. They have electrons. They have their valence shell filled up. The oxygen is happy. Its valence shell is filled up. But because the protons are so powerful, all the electrons are sort of dragged down towards it. They don't ever get there, but they're pulled enough so that the ends of the molecule are slightly positive on the hydrogen side and slightly negative on the oxygen side. And what will happen then is that leads us into what's known as the third category, the hydrogen bond. Because of the unequal sharing of electrons, now they're still shared, but because of the unequal sharing of electrons, the positive ends of a water molecule are attracted to the negative ends of a water molecule next to it. So the positive hydrogen ends are attracted to the negative oxygen ends. And so each positive hydrogen can bond with a negative oxygen, like you see here in the illustration. These are hydrogen bonds. There's a positive hydrogen attracted to a negative oxygen. There's another one, and they form this structure called a lattice work. It forms this large, very large, three-dimensional shape. This is what, among other things, this is what gives water some of its unique properties. This is why water is held together. You know, consider the fact that if you take a pan of water and put it on the stove and turn the heat on, it doesn't boil instantly. It takes time to get that water moving. The heat causes the water molecules to move, which eventually starts breaking these bonds between the water molecules and eventually starts boiling. And if you boil it long enough, you'll boil all the water out, you'll convert it all to water vapor, and it'll be gone. The hydrogen bonding between the water molecules is what makes water a liquid. It's held together in its consistency. You know, so because water molecules are a polar molecule, they have a positive and a negative end, and positive ends will be attracted to negative ends and form hydrogen bonds. Now, is water the only thing we have a hydrogen bond in? Actually, no. We use hydrogen bonds to give very large molecules very unique shapes. Proteins, as we'll see later on, proteins have very specific shapes designed to do what they do. You know, like, you know, some proteins act like chemical messengers. Some proteins act like a lock and a key. Some proteins will turn on a cell or turn off a cell based on their unique shape. And the shape of the protein is dictated by hydrogen bonds between the different molecules, between the different atoms, between the different molecules making up the protein. So they'll twist it around into whatever shape it needs to be in. Our DNA, for example, is twisted into a double helix. You know, it's like a double spiral stairway structure. And part of that structure that gives us that spiral is hydrogen bonds, little weak hydrogen bonds holding the DNA, the 6-foot-long molecule together. And this is what a water molecule looks like right here. And I don't know if there's sound or not, but we'll know here in a second. And there isn't. But a water molecule is a polar molecule with the hydrogens, the electrons of the hydrogen being pulled towards the oxygen end because of the 8 protons here and only 1 proton here. So the electrons are drawn towards the middle. It is unequal sharing of electrons. And so the oxygen end, because it's pulling all the electrons towards it, becomes slightly negative, and the hydrogen ends become slightly positive. We haven't lost any electrons. We haven't gained any electrons. We're still sharing electrons around each atom. But the pull is slightly greater towards the negative end, the oxygen end. But the water molecules then can combine. Every water molecule can combine to at least 3 other water molecules. The hydrogens can combine to the negative oxygens of adjacent molecules, and the negative oxygen can combine to a positive hydrogen of an adjacent molecule. And so we get this type of structure. Well, imagine you have billions of these structures in water holding it together, which is why water has this ability to be cohesive. It sticks together. It doesn't, when you pour water out of a glass or turn on the faucet, the water molecules don't fly off into space, they stay together. So because of this structure. Yeah. Now, last thing to talk about, because I've thrown a lot at you today, this is called van der Waals attraction. Van der Waals attraction is something we see in solid fats. Things like butter and lard, animal fat, things that, fats that are solid at room temperature. Fats are made up of 3 long chains, what we call fatty acids. And these fatty acids are constantly, moving around in each chain. And as they move, the charge on each part of the chain becomes slightly positive or slightly negative, and a chain next to it can become slightly positive or slightly negative. If they line up just right with a positive and a negative, they're going to stick together briefly, and then they're going to let go. And then they're going to stick together, and then they're going to let go. Because they can stick together and let go and stick together again, that makes things like animal fats solid at room temperature. Van der Waals attraction is a temporary attraction. It is the unequal sharing of electrons that occurs in transition. But it describes why fats, animal fats, are solid at room temperature. Plant fats, oils, don't have that attraction. The molecules are, the long chains of fatty acids are lined up further apart. They have little bends in them too. And so animal fats are liquid at room temperature, whereas animal fats are solid at room temperature. Plant fats like oils are liquid at room temperature, thanks to van der Waals attraction. Van der Waals attraction, van der Waals bonding is very, very weak. It's about 1/100th of the strength of a covalent bond, but it does make fats solid, animal fats solid at room temperature. So, okay, and I think that's where I'm going to stop at this point. Any questions? You better try chat, because I don't know if I can hear you, if you have any questions. Okay. Again, lab, today we're going to go into the second part of Unit 1. We're going to look at cells, and we're going to look at mitosis, and we'll talk a little bit about diffusion and osmosis. And then next week, we're going to start looking at bones. Probably the week after that, we'll have our first lab test. So, and I will find out today why I can't hear anybody. So, and I will see you all later. Thank you for being here today.